You open the what's that like or understand like that portion to what's the some yeah. Yeah, I saw it. I'm not getting seriously. It's like too shocking. I think I can solve or something. But you can get it.
All right, so let's go and get started. All right, good afternoon, everyone. How's everyone doing? Good, everyone have a good weekend? Good to hear. So over the weekend, my wife had some work to do in LA, so we ended up visiting a hotel called the Biltmore. So if you don't know, it's a historic hotel in LA. It's where the Academy Awards used to be, so a long history with show business. And I think nowadays it's more famously known because Taylor Swift actually filmed a music video there. My wife's a big fan of Taylor Swift, and so when we were driving there, she was kind of making fun of people because a lot of people go to this hotel and they kind of recreate scenes from the music video. And the whole time I was just like, because I knew that when we would get there, she would want to do the exact same thing, and we definitely did. So. So not only are there pictures of her, recreating, there's also pictures of me on her Instagram recreating scenes from Taylor Swift. But that's why you will never know my wife's name or her Instagram handle, because can't afford you guys seeing those pics. Okay. All right. So some announcements. So homework 2 I posted on Friday. So I think some of you guys have already seen that. I think I've already gotten a couple questions. I've decided, so this section on constraint optimization, I want to take my time with it a little bit more. So homework 2 is just going to be on unconstrained optimization. So all the classical method stuff we covered last week. So you guys already have everything that you need to know for the homework, and so you don't need to wait on any of the lectures this week. So the homework is going to be due next Tuesday, September 24th. Okay. I think it kind of breaks up the assignment a little bit more too, because if I put the constrained optimization stuff, it just ends up being a massive homework assignment. So I thought I would just give you the unconstrained stuff first, have you guys work on that, and then next week I'll have another homework assignment for the constraint stuff, and that'll take us to about the midterm exam. So midterm exam is probably going to cover homeworks 1, 2, and 3. That's my okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off last Thursday. And so we were going over kind of our introduction to constrained optimization, specifically constrained optimization using classical techniques, right? So like I mentioned, everything up until the midterm, we're going over these classical techniques. The reason we're going over the classical techniques, part of it is kind of historical. This is kind of the origination for a lot of the modern techniques. Even though these classical techniques are kind of outdated, no one really uses these anymore. But it's important to learn these things to get the foundation, so that when we get to the MATLAB and the programming and the modern techniques, they'll have a lot more context. Okay. And so what's different about the optimization problem we're doing this week is that not only do we have an objective function to define the performance of our system, we also have constraints, right? So just to refresh your memory, constraints. Constraints are simply just limitations on the possible or valid values of the design variables in your optimization. Right, because in most in most situations that you're going to be tackling and you're going to be using optimization in practice, there's always going to be some constraints. Some of them are going to be fairly obvious. Most of the time we limit ourselves to strictly positive numbers, but some are a bit more limiting as well. Right, so learning how to deal with constraints in optimization is a really important skill, and there's lots of different ways that we can kind of deal with these things. And so to start with, we're starting kind of simple. And so we're starting strictly with equality constraints. Because most of the time, for, and for this class, all the time, all the constraints that we're gonna be dealing with, they're gonna take the form of some kind of mathematical algebraic equation, okay? So equality constraints describe constraints that are, constraints that have equations that strictly use an equal sign. And so the standard form for these constraints is the following. So in this standard form right here, G is just a generic function. So that generic function, that's the mathematical form for the constraint. This X vector here, of course, this is our vector of design variables. And of course, in the standard form, we manipulate the equation algebraically so that it equals 0. Okay. So standard form, we have to have equals on, we have to have 0 on one side of the equal sign. This standard form, it's for the first part of the class today, it's not going to be really that important to have our constraints in standard form. In fact, for the direct substitution method, most of the time you move it out of standard form right away. But once we get to Lagrange multipliers later on in the class, it's going to be really important to have this in standard form. So I thought I'd mention it again at the beginning of class. Okay, and so what's unique about equality constraints is that they basically define a relationship that must be satisfied in your optimization. Okay? And so if you recall from last Thursday, another name that you can have that people call equality constraints is these are hard constraints or hard limitations, something that has to be true, in your optimal result. So no matter what you get for your optimal solution, you're not going to have a valid solution unless the equality constraint is strictly satisfied. Okay. And so, when you see that, you might think that equality constraints, they're very rigid, they're kind of hard to work around, but we can actually use this to our advantage. And so, with that knowledge that, the equality constraints must be satisfied, we can actually use this to make our problems a little bit easier. And so that was the first technique that we started going over last Thursday, which was the technique of direct substitution. Remember, the idea behind direct substitution is that you're going to take your constraint, which is a equality relationship, and then you're going to manipulate it in a certain way so that you can take that constraint and directly substitute that into your objective function, right? And hopefully the idea with that is that it reduces the dimensionality of your problem. Instead of solving for 3 variables, maybe you're only solving for 2, And then it just kind of makes the whole thing easier for me. Okay. All right, so that's kind of where we left it off. And so, I wanted to kind of summarize that before we jumped into an example. So are there any questions on this? Okay, all right, so let's jump back into the example that we were going over last time. Okay. So the example that we were doing last time was that, we were curious about, if you had a sphere, right? What's the largest box or the largest kind of rectangular kind of brick that you can fit inside that sphere in terms of volume? All right, let's see if I do a better job of drawing the box this time. Okay, so we have our sphere. And we have our box on the inside. A little better this time, at least the box is inside the sphere, but it looks like, we have a little bit of space to go. Okay. All right. So what's kind of strange, I mean, the question I think is fairly straightforward, but the way that we're parameterizing this is a little bit strange. So let's go over that again. Okay. Remember, the way that we're parameterizing this is that we're assuming that, we have our origin of our Cartesian system right in the middle of this box, right? So the origination of, let's say x-axis is this way, let's say y-axis is this way. And z-axis coming out in front, okay? So that origin is right in the middle of the box, both the box and the sphere, and so they're both kind of centered on the same. Okay. And so, when we are asking ourselves, what's the largest box, what we're interested in is the dimensions of the box itself. Okay, so we have 3 dimensions. So this dimension right here, call this x2. Or more specifically 2x2. This length right here, we'll call this 2x1. And then the depth into the page, we'll call that 2x3. x1, x2, x3, those are our design variables. Now, the reason, we have, the 2's out in front, so that might seem a little bit strange. Remember, the way that we're kind of parameterizing is based on the origin, right? And so x2 or a single design variable x1 is the distance from the origin to the edge of the box. So kind of the half edge length is x1, the half edge length is x2, is because that's the distance from the origin. If you just go straight up or straight to the right or straight out of the page, that's how long you have to travel to go from the origin to the edge. Okay. All right, and so we have our parameterization here, right? So we know what our design variables are. Let's define our objective function, and let's define our constraint. Okay, so let's start with the objective first, right? And so based on the problem statement here, right, we want to find the largest box. And so our objective function has to capture that, has to be able to rate the size of the box. Okay. And so our objective in this case, the way that we're going to judge size is that we're going to do it based on volume. We want to maximize the volume. So what we're basically saying is that more optimal designs or designs that we desire more are going to have a bigger volume than other ones. Okay. And so we can compute that. And so the volume of our box in this case, knowing that each side length is 2x1, 2x2, 2x3, we're just going to multiply all of the side lengths together. So it's going to be 2x1, 2x2, and 2x3. And so we multiply all those together, we get 8x1, x2, x3. And so this is going to be our objective function. Our objective function is going to be just purely the volume of the box. Okay. Now, if this were just, if we didn't have any constraints, and so, we just had an objective, what are the dimensions of the biggest box ever, right? Then, the easiest thing to do would be to set x1, x2, x3, all of them equal to infinity, right? Because that's, if you have a box with an infinite edge length, then that's the box with an infinite volume, right? Easy. But the reason this problem is interesting is because we do have this constraint, and our constraint is that our box has to fit inside the sphere. All right, and so we need to encapsulate this constraint into a mathematical equation that we can use. Okay. All right. So the way that we're going to do this is we're going to take advantage of kind of how we parameterize this problem. Okay. Remember the way that we parameterize it is that we put the box centered right at the origin. Okay. If you think about, if you're walking from the middle of the center of a cube or the center of the block, right? What direction that you have to walk in order to reach the longest path possible without exceeding the box, right? What's the longest dimension in a box space? It's diagonal, right? And so if we walk from the middle of the box to one of the corners, that's kind of the longest dimension within the box itself. And so what we're basically assuming here is that if all of the corners fit inside the sphere, then we're good, right? Because then if all the corners fit inside the sphere, then all the other parts of the box are going to fit inside the sphere as well. So what's the distance between the origin of the box to one of the corners, right? And so because we parameterize this in this way, the distance from the center of the origin to one of the corners, we're just going to use our distance formula. X1 minus 0 squared plus x2 minus 0 squared plus x3 minus 0 squared. Okay. So that formula right there, that's the distance from the origin of our system to one of the corners of the box, right? Because we know one of the corners is located at x1, x2, x3, and the origin is of course 0, 0, 0. And so based on our constraint and knowing that our box, or excuse me, our sphere has radius 1, then this distance from the origin to the corner of the box has to equal. All right, so let me clean this up. Let me just put it all into one single line. And so our constraint in this case is that x1 squared plus x2 squared plus x3 squared has to equal 1. All right, any questions? Any questions on the form of the objective function in this case, or the form of the constraint? Okay, good. All right, so we're not going to use it. We're not going to use this for this problem just because we're going to do direct substitution. But let me show you how to put this constraint in standard form. So this is kind of just like an aside, right? So, with direct substitution, we don't really use standard form, but it's good to kind of think about it, kind of get some practice with it. And so remember that with standard form, we have to have 0 on one side of the equal sign, right? And so the easiest way to accomplish that is to take this 1 and subtract it into the other side, right? And so the standard form for this constraint would be x1 squared plus x2 squared plus x3 squared minus 1 is equal to 0. Because what we can say from this is that then we now have the constraint in the form of g of x1, x2, x3 equal to 0. Where that g function is that x1 squared plus x2 squared plus x3 squared minus 2. Okay. Okay. But again, we're not using that for this problem, but I thought I'd mention it just because we're going to be using it. Okay, but the way we're going to solve this one is we're going to use direct substitution. And so in direct substitution, we're going to take our constraint, we're going to manipulate it algebraically in a certain way, and then we're going to plug it back into our objective function. Okay. So that's the whole idea with direct substitution, right? And this actually helps us out quite a bit because if you look at our original optimization problem, we have 3 design variables, right? We haven't done a problem with 3 design variables because honestly, it's a big hassle to do 3 design variables. And so the way that we're going to make this easier is that we're going to take our constraint, we're going to solve it for one of the design variables, plug that back into our objective function, and then we're going to be solving just a problem with 2 design variables instead of 3. Okay. So let's go ahead and do this. Now you can solve for when you're using direct substitution, there's no right way to do it. There are easier ways to do it for sure. But which variable you end up plugging in, it's up to you. And if you do everything correctly, you should still get the same result no matter which direction that you do. Okay. And so looking at our constraint here, right? Our constraint is x1 squared plus x2 squared plus x3 squared is equal to 1. We can solve for any of these variables, and in fact, this equation is symmetric on all 3, and so it doesn't really matter which one that we solve for. Okay? And so I'm just going to pick one. So let's pick x3 to solve for. Let me write down the constraint one more time. So our constraint. Our constraint is the following. Okay, so x1 squared plus x2 squared plus x3 squared is equal to 1. And so I'm going to solve this equation for x3. Okay. I mean, obviously right now we won't be able to compute the value for x3, but all we want right now is an expression for x3 that we can plug into our objective. Okay, so first thing I'm going to do is I'm going to subtract x1 squared and x2 squared from both sides of the equation. And so if I do that, then I get x3 squared is equal to 1 minus x1 squared minus x2 squared. Okay. So now we have this equation where x3 is on one side of the equal sign by itself, which is good. But of course, you know, we don't have x3, we have x3 squared. So in order to finish this up, we have to take the square root of both sides. And so we take the square root of both sides, we get x3 is equal to square root 1 minus x1 squared minus x2 squared. Okay, so now let's plug this into our objective function and then we can go. Okay, so our objective function in this case is simply just the volume of the box, and so we have f of x1, x2, x3, 2, 8, x1, x2, x3. Let's take our result for x3 and plug it into this equation here. What that does is that it effectively eliminates x3 from the equation. And so now we're only going to have an equation or function of two of our design variables, x1, x2. Okay, so now our objective function is 8x1, x2 times quantity square root 1 minus x1 squared minus x2 squared. Now it is messier, you know, there's no getting around that for sure. But you know, the fact that we've reduced this from a 3D problem to a 2D problem saves us a ton of work. All right, any questions on how we got here? Okay. All right, so but this is kind of as far as we can take it in terms of simplification. So now the only thing left to do now is to solve. Let's go ahead and solve using the classical methods. Okay. Now, you know, we still have a multivariable optimization here, so we have to dive into partial derivatives. Okay. All right, so the first thing we're going to do is we're going to take the first order partial derivatives, and so we're going to take partial f partial x1 and partial f partial x2. Now you have to do a little bit of product rule, a little bit of chain rule here. So there is some calculus that needs to be done here. Okay. Let me do this just to make it a bit easier. Let me split it up into these two terms. Because the first thing we need to do is to take product rule, right? And to do product rule, remember the way product rule works is that if you have a product of two quantities that both have the variable that you're taking the derivative of, you take the derivative of the first and the second plus the derivative of the second times the first. Okay, so let's do derivative of the first expression there, right? So our first expression is 8x1, x2. So the derivative of that with respect to x1 is just 8x2. And then for the second one, we're just going to leave it alone, right? We're just going to multiply this by square root 1 minus x1 squared minus x2. So that right there is derivative of the first multiplied by the second. Okay. Next, we're going to do derivative of the second multiplied by the first. But just to kind of keep things in order, let me drag the first part down. So the first part is simply just going to be 8x1, x2. Okay. So that's the first term, but we just didn't take the derivative of it at this time. And now we have the derivative of the second part. Now this gets a little bit tricky because we have to do a little bit of chain rule here. Okay, and so remember, when you have a square root is nothing more than just having something to the power of 1/2. Right, so let me rewrite this as 1 minus x1 squared minus x2 squared raised to the 1/2 power. Okay. Because now that we have it like that, we can just use our typical, power rules of differentiation, just with some added chain rule. Okay, so for chain rule, remember you take derivative of the inner times derivative of the outer one. Okay, let's do derivative of the inner part first. So the inner part is simply quantity 1 minus x1 squared minus x2 squared. Okay, so derivative of that inner part, right? Remember, we're taking the derivative with respect to x1. So two of those terms are going to go away. The 1 is going to go away. The minus x2 is going to go away. And all we're left with is a minus 2x1. Now we have the derivative of the outer part, which is the part that's under the square root. Okay, so we're taking the derivative of something with the square root, so we end up with a 1/2. The 1/2 comes out because of the power of 1/2 out there. Okay. And then we have that quantity, then we're going to subtract 1 from the exponent. So we subtract 1/2 minus 1, we get a minus 1/2. Okay. So that's going to be multiplied by quantity 1 minus x1 squared minus x2 squared raised to the minus 1/2 power. A lot of calculus screw up there, but hopefully it was kind of clear how we got that. Any questions on how I did the derivative of that second term? Okay. All right, so let's go ahead and simplify this. So the good news is that after we've solved the first partial derivative, the second partial derivative it's kind of its for x2 is kind of its mirror image. But let's simplify this. Let's clean up a bit first. Okay, so to clean this up, first thing I'm going to notice is that I have an 8x2 on both of these terms, and so I'm going to factor that out of the expression here with 8x2. And then we're left with everything on the interior. So everything on the interior, we have a square root. Or let me change things to their to the exponent form. So we have quantity 1 minus x1 squared minus x2 squared raised to the 1/2. Okay, so that's that first term. After I factor out the 8x2, all we're left with is just the square root term. Then we have a minus. We have an x1 squared, right? So we have x1 and x1 here. So those are going to be combined to become x1 squared. The 2 and the 1/2 are going to cancel each other out. So this 2 is going to cancel out with this one. And then all we're left with is 1 minus x1 squared minus x2 squared raised to the minus 1/2. All right, so that's our first partial derivatives. Let's go ahead and compute the second one. Second partial derivative is going to be partial f partial x2. We're just going to go through the exact same process, except we're going to be taking derivatives with respect to x2 instead. Okay. And so same thing, we're going to use our product rule and our chain rule at this point. And so the first this first one is going to be 8. We take the derivative of that with the first parentheses, the first red parentheses there with respect to x2. So we're all left with an 8x1 times quantity 1 minus x1 squared minus x2 squared raised to the 1/2 power. Then we're going to take the derivative of the second part there, and this one we use the chain rule. Okay? But first, we bring the first term down, so we have 8x1 x2. Then we have minus 2x2 multiplied by 1/2 multiplied by 1 minus x1 squared x2 squared. So kind of like the mirror image of kind of what we had above, just x1 and x2 are just swapped. Okay. So once again, we can simplify this. I'm going to take the 8x1, I'm going to factor it out. And all we're left with on the inside is a 1 minus x1 squared minus x2 squared raised to the 1/2 power minus x2 squared 1 minus x1 squared minus x2 raised to the -1/2. So that equation combined with the top one up there, those are the two equations that we. And of course, I forgot the most important part. Both of these equations are equal to 0. Okay. Because remember, in the classical methods, we take our first order derivatives, we set them equal to 0, and we solve this system of equations for our design variables, and that gives us our optimal. Okay. Any questions on this from here? All right. So now that we have these two equations, we need to solve them for the values of x1 and x2. That seems quite daunting. I'm aware of that. There's a lot of radicals in there. Okay. But there's actually, when you're dealing with square roots, and we have some square roots in the numerator here, some square roots in the denominator. There's kind of a simple trick that you can do. And also it also kind of helps us that we have these equations equal to 0. Okay. So to simplify these equations greatly, what I'm going to do is I'm going to multiply both equations by square root 1 minus x1 squared minus x2 squared. So what I'm targeting with this move, what I'm targeting with this move is first of all, I want to eliminate all the square roots from these equations. Okay, so we're going to take advantage of the fact that we have zeros on both sides, and so that kind of gives us free reign to kind of do what we want algebraically to both sides. I'm trying to be better with this in general, and so, for these kind of long examples like this, whenever I do a step, I try to kind of write down or at least try to explain kind of every step that I do, so. Trying to be better with that, because I know that's kind of a criticism that I've had in the past, and so. If at any point, I'm doing an example or explaining something and you're not sure how I went from like step A to step B, or a lot of times like from step E to step F, right? Just let me know, because sometimes I kind of skip steps in my head. And some things can kind of move a bit too quickly, so, but I'm trying to be better, Okay, so by multiplying both sides by square root 1 minus x1 squared minus x2 squared, that gets rid of a lot of terms for us. Okay, let's start up here. So the two terms that I'm really targeting here are this one and this one. Okay. So by multiplying by that expression there, I'm going to distribute that through and kind of cancel a lot of these terms out. Okay, so let me write down that first equation again, just so it's a little bit easier to see what I'm doing. So that first equation was 8x2 multiplied by quantity 1 minus x1 squared minus x2 squared half minus x1 squared. Quantity 1 minus x1 squared minus x2 squared raised to the minus 1. And of course, this whole thing's equal to 0. All right, so let's multiply this entire thing by quantity 1 minus x1 squared minus x2 squared. So primarily, this move is going to target this term and this term. Okay, so let's talk about what it's going to do to the first term first. Okay. So we're taking a square root quantity and multiplying it by exactly the same thing. And so when you multiply two quantities that are square rooted and they have the exact same thing underneath the radical, you just end up with just whatever's just underneath the radical. So after multiplying, this just becomes 1 minus x1 squared minus x2 squared. Okay. So we kind of eliminate the radical. Okay? So we have two things multiplied with an exponent of 1/2. Those 1/2s add together, and so we end up with something with an exponent of 1. Okay. We can actually apply that same logic here, right? So we have two quantities that have the exact same, expression underneath the radical, except now we're multiplying by something with a minus 1/2, right? So minus 1/2 added to positive 1/2, that's just going to be 0. So after multiplying that, that quantity there, the second one is just going to end up being 1. Okay, so we effectively cancel it out completely. Another way that you can look at it is that, remember, when you have a negative exponent, that's the same thing as, putting it in the denominator, right? So we take the reciprocal. If we have the exact same thing in the denominator as the numerator, those things cancel out and become. Okay, so by doing that, we end up with actually a pretty simple expression here. So we have 8x2 divided by 1 minus x1 squared minus x2 squared, okay, minus x1 squared. And of course, all this is equal to 0. We have two x1 squareds in the parentheses there. So we have 8x2 divided by quantity 1 minus 2x1 squared minus x2. One last thing before we move on to the second equation is, we can kind of, just because of the physical nature of the problem, we already kind of know that all the x variables are going to be greater than 0. It doesn't make sense, if you have one of the box dimensions be 0, then you have a box of 0 volume, which, there's no way that's the optimal solution, right? And so since we know that x2 is greater than 0, we can actually divide by that as well. Okay, so I'm going to divide both sides by 8x2. Once again, kind of taking advantage of the fact that, we have a null equation here, we have an equals 0. And so, we're going to just kind of do algebraic expressions with impunity on the left, and it's just all going to cancel out on the right. Okay. And so by doing that, we get 1 minus 2x1 squared minus x2 squared. 0. Which of course is a much simpler expression to work. Okay, so let's do the same thing with the other equation. Okay, so our other equation, let me write out the whole thing again, 8x1 multiplied by quantity, 1 minus x1 squared minus x2 squared, raised to the 1/2 power, minus x2 squared, 21 minus x1 squared minus x2 squared, raised to the minus 1/2, and then of course all equal to 0. Okay, so we're going to do the exact same thing to this equation here. So we haven't solved anything yet. Let's take a step back. So all I'm doing at this point is just kind of simplifying these equations and making them a bit easier for us to solve. Okay. But since this equation is very similar to our first one, let's simplify it in the exact same way. So first thing I'm going to do is I'm going to multiply both sides of the equation by square root 1 minus x1 squared minus x2 squared. Let's also, apply our assumption that we know that x1 is going to be greater than 0, so we can divide both sides by 8x1. And so doing that, what that gives us is 1 minus x1 squared minus x2 squared minus x2 squared is equal to 0. Right, so I cancel all the radicals, I cancel the denominator, cancel that 8x1. Okay, so a lot of simplifications here. And so all we're left with is 1 minus x1 squared minus 2x2 squared is equal to 0. Okay. So now we have these two underlined equations. This is going to be a lot easier for us to solve for x1. All right, any questions on how we got here? Okay, cool. All right, so let's go ahead and solve these equations. Okay. So these two equations are actually very symmetric, and so you can kind of go about this any way that you want. So let me solve this equation for x1 squared, and let's plug that into the other equation. And so to solve this for x1 squared, I'm going to take this and move it to the other side of the equation. And so we have x1 squared is equal to 1 minus 2x2 squared. Let's plug that into the equation up there. So plugging it into that equation up there, we have 1 minus 2x1 squared minus x2 squared. Okay. Plugging in for x1 squared here, we have 1 minus 2. Just want to do 1 minus 2 x2 squared minus x2 squared is equal to 0. All right, so let's just distribute and simplify it. It's just an algebraic equation at this point. We have 1 minus, we distribute that 2 inside, so we have a minus 2 plus 4x2 squared minus x2 squared. Oh. All right, so let's combine like terms, and so we have 1 minus 2 is minus 1. We have 4x2 squared minus x2 squared, that's going to give us positive 3 x2 squared is equal to 0. Let's add 1 to both sides of the equation and then divide by 3. We have x2 squared, 2 third. We take the square root. And finally get x2 is equal to square root of 1 third. So now that we have the result for x2, let's go ahead and plug this back in, solve for x1. So we know from our equations that x1 squared equal to 1 minus 2 x2 squared. So we plug in x2 squared, so we know from this expression here x2 squared is equal to 1 third. We have x1 squared equal to 1 minus 2 times 1 third. We just work out the math, we take the square root. We see that x1 also has to equal square root of 1. So it's been a lot of work to get to this point. A lot of optimization problems are kind of like this. But once you find one optimal value, so once you find the values of one design variable, the rest kind of just fall into place just right from there. Because the last one that we need to solve for here is x3, right? So remember, x3 wasn't part of the classical method that we just did. The value of x3 is going to be defined by our constraint. Okay, so remember our constraint. This is way back up there, right? So our constraint of this case for this problem is square root, or x3 is equal to 1 square root of 1 minus x1 squared minus x2 squared. We know what x1 is now. We know what x2 is. In fact, we know what x1 squared, x2 squared is. So let's just plug those values in. We know that x3 is equal to 1 minus 1 third minus 1 third. And so, of course, we can do the arithmetic, and this result probably is not surprising, given the first two results were also square root of 1/3, right? And so x3 also is going to be square root. Okay. All right. And so that's it. And so that's it. And so that's our optimization problem. So, if you were to make a box. If you were to make a box, and this box is constrained by the fact that it has to fit inside a sphere of radius 1, then we know that the biggest box that can do that is one where each side has length 2. So that's the biggest box, or the highest volume box that can fit inside a sphere of radius. All right. Any questions on this? All right, so that's the direct substitution method. I think honestly, for the most part, if you have a problem with equality constraints, mostly you're going to be using the direct substitution method, or at least the problems that I'm going to give you, mostly you can solve it with direct substitution. So definitely don't be afraid to use this method. I'm going to teach you one more method just because it does kind of lead into some stuff that we're going to do later on. But direct substitution is probably the most straightforward with the two. A question in the chat. Hang on. See, is this possible to do for largest volume? This is largest volume. Yeah. So of course, one step that we're skipping at this point is that if we truly wanted to confirm that this was a maximum, then we need to compute the Hessian matrix, and we need to determine if it's negative definite. So that's something that we absolutely need to do. But just kind of intuitively, this kind of we kind of already know that this is a maximum. Because we can't make this cube any bigger without exceeding past the sphere, and it's definitely not a minimum either, right? And so the minimum box, the minimum volume for something that can fit inside a sphere would be a box of volume 0, right? It's kind of a trivial solution. And so for this one, just based on kind of intuition, we know that this result is a maximum. Oh, surface, yeah, you can definitely redo this problem with surface area. Yeah, so what that would do is that would change your objective function. In fact, you're kind of getting ahead of me a little bit. I was thinking about adding that exact problem on your next homework assignment. So I'm going to work on that this week. And so one other way that you can kind of spin this problem is that instead of maximizing volume, right? So our objective function was based on the volume of the box right here, right? And so if you instead wanted to maximize surface area, your objective function would then be different, right? And so objective function would be, so you have the areas of each of the sides times 2. 2 times 4, x1, x2 plus 4, x2, x3 plus 4, x1, x3. So you can go through the exact same process, right? And so your constraint would be exactly the same. It would have to fit inside a sphere of radius 1, but you would do it for a different objective function. So that, of course, is going to change your derivatives. That's going to change, the optimal. It might be the same actually, but something interesting to see. So I'm going to work that through myself, and then that problem is likely going to show up on. All right. Any other questions on this example before we move on? Okay. All right. So the last thing I wanted to introduce today, where this is a discussion we're definitely going to continue on Thursday as well, is another method for solving optimization problems with equality constraints. Right? And so that is the method of Lagrange multiplier. So Lagrange multipliers. I would say this is kind of the more traditional, this is the more traditional way to solve problems with equality constraints. For the problems that we're going to be doing, you can definitely solve them with Lagrange multipliers. It just kind of it just just for the nature of the problems I'm going to give you, it just kind of ends up being direct substitution with extra steps. But the reason I'm kind of introducing Lagrange multipliers to you is more just as an introduction of kind of a method, right? Because this form and this kind of framework is going to be used for other things that we're going to do. Okay, so basically the idea with Lagrange multipliers is that instead of solving the constraints and the objective function kind of separately, with Lagrange multipliers, we aim to kind of combine them all into one. Basic idea is to take each of your equality constraints and add them directly into your objective. And so by doing so, you're going to have a sum. You're going to have a sum of multiple things, right? The sum of the objective function and your equality constraints, we kind of call it a new term, and so we call that the Lagrange function. Okay, so the Lagrange function kind of looks like the following. So we give it the symbol L. Okay. This function here is going to be a function of a few things, and so of course, what's going to be there is going to be your design variables. We call it the Lagrange function like it's a new thing, but you can almost think of it as like your objective function plus, right? So your objective function, original objective function is still going to be there. It's just that now we are including the constraints as well. The other thing that this is a function of is something that we haven't seen before, because it's unique to this technique, is these things that we call Lagrange multipliers. And then we give those a symbol lambda. So we'll talk about what those are in a second. Okay, so how you form the Lagrange function is that you take your original objective function. So there's f of x, x right here. This is our original objective function. And then to that, we're going to add a summation of all the constraints in standard form. Okay, so to this, we're going to add summation I is equal to 1 to m. Or little m right there, that defines the number of equality constraints that we have. And so that summation is going to be a product of the Lagrange multipliers, all the lambdas, multiplied by each of the equality constraints. This m right here, this is the number of constraints. G right here, these are our equality constraints in standard form. So that right there is our Lagrange function. Okay. Now, this looks quite a bit more complicated, right? And in fact, one concern that maybe have here is that, by changing the function here, right? It kind of almost seems like, we're changing the optimization itself. Because the idea with this Lagrange function and the reason we kind of form it in the first place is that, now we can, basically apply our classical methods to this equation itself, right? And so we don't have to do any kind of substitution. And so once we kind of form this Lagrange function, we can treat it as a classical optimization on its own. And that's kind of that was kind of the motivation of forming this technique is that, when you have constraints, you shouldn't, if we can kind of reform the problem in a way where we can solve it using the methods that are kind of tried and true, then that's great, right? And so by adding the constraints directly into the objective function, then we kind of account for them on the one hand, but also we can solve it using our previous techniques. Okay, so the idea is to have kind of one kind of monolithic equation that we're going to solve for the whole. But one concern that you might have is, wait a minute, if we're adding our constraints to our objective function here, doesn't that change the nature of our problem, right? Are we still going to get the same optimal result if our objective function itself is going to change? Technically, yes. So technically, if you make any significant changes to the objective function, it is going to change your problem. It's going to change the optimal result. But actually, if you're doing this, right, you're just adding the Lagrange terms themselves, you're actually not changing the objective function at all. In fact, I would make the argument that this Lagrange function is actually, it's going to behave identically to our original objective function. It's not going to seem like it, and then once we start doing example problems, it's definitely not going to seem like it because it's going to add a lot more work. But the key to this whole thing is the fact that in order for this to work, we have to put our equality constraints in standard form. Remember, standard form is that we move kind of all of the design variables and all the terms to one side of the equal sign, and then the other side is just going to be 0. For standard form, our standard form is simply g of x is equal to 0. Okay. And so if you take that in mind, if you kind of account for that and know that we're adding all of these constraints to standard form, essentially what we're doing is we're just adding a bunch of zeros to the end of the equation, right? And so adding zeros mathematically doesn't change an equation or change any kind of result. And so technically, we're adding a lot more variables, we're adding a lot more things to the equation. you know, technically, they're all just a bunch of zeros because they're all unstable. Okay, any questions on this? Okay, so I just wanted to introduce the idea today, and so you know, we'll definitely pick this up on Thursday. There is kind of one other thing that I want to go over today, and I should have covered it at the beginning. So I did grade your guys' homework once, but I did want to address one thing that I kind of saw pretty consistently in most homeworks. And that was with problem 4C. Okay, so if you don't remember, you know, problem 4C is it was a plotting problem. And so what I asked you to do is I gave you an objective function and I gave you some constraints. And I asked you to plot out the objective curves and as well as the valid region. And specifically, you know, the part that I kind of saw a lot of people struggling with was this idea of, you know, plotting the objective curves because it was a multi-dimensional optimization. Okay, so just to kind of refresh your memory, the objective function for this problem was f of x1, x2 is equal to 15x1 minus 12x2 squared plus 10. Okay. All right. And what I want you to do is that I want you to plot the objective curves on a 2D plane. Okay. Okay, so remember, you know, when you have a two-dimensional optimization, you know, oftentimes we like to plot quantities against each other, right? I think it may be a little bit confusing just because of the variable names that I use here. I use x1, x2. Okay. But when I ask you guys to plot, you know, I'm asking you to plot one design variable with respect to the other. And so I think what a lot of people did was that they took this objective function and then they kind of threw it into MATLAB, but they threw it into Desmos and tried to kind of plot that, and you kind of ended up with something kind of strange. Right? So what I actually want you to do in this case is that, you know, if you look at our bounds here, or you look at our axes, our vertical axis is x2, our horizontal axis is x1. Okay. And so to plot something, you need to have an expression of x2 is equal to some function of x1. So in other words, you know, you need to manipulate the objective function so that x2 is kind of on one side of the equal sign and, you know, everything else. So of course, what this means is that you have to manipulate the objective function a little bit. So let me take this objective function and solve it for x2. Okay, assuming just for a second that f is just a constant value. And so if we do that, I'm going to move 12x2 squared to the other side. I'm going to move f to the other side over here. Okay, we have 12x2 squared is equal to 15x1 plus 10 minus f. Then what you can do is you can divide both sides by 12, take the square root. X2 is equal to square root over 12, 15x1 plus 10 minus f. So when I asked you to plot objective curves, this is the function that I actually wanted you to plot. Okay, so that's how you got kind of those relatively straight kind of you know, kind of slanted lines. Okay? And the way that you obtain different curves, that you're going to plug in different values for f. Okay. But that should give you a line that you could plot in the x1, x2 line. So yeah, I wanted to make sure I go over that just because I saw this on you know, quite a lot of the homework, so I wanted to make sure. All right, any questions on this or just anything we covered today? Okay, all right, so thank you guys for coming today. When we pick this up on Thursday, we'll dive deeper into the Lagrange multipliers and see how that method works. All right, so thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Jason.
Yeah.
Yep. Yep. And mine is around 7. Just make it quite about. Yeah. October 10th. Okay. Okay, yeah, if it's if it gets to that, just let me know, and then we can arrange it. Yep.
The class after. I agree.
I just
I took a picture, just like, see that.
you also got to think about it. It's 2 cases on the body. I can love someone else. Is if you get hit in the sternum or the liver, if you get or a
You're
venison,
not trying to injure my liver.
Yeah.
And you didn't aim for the sternum,
yeah, well, if I hit right here,
so I accounted for everything.
Yeah.
Checkmate.
double shot.
You only did one check. And I already went for your chin.
Mike Tyson.
Just check this out.